figuring out how things work and what they're like. All of the things we'll cover in this class were discovered, investigated, and figured out using a relatively recent method called the scientific method. Much of the technology and high standard of living people in the US experience, compared to elsewhere in the world, is the result of using the scientific method to figure out physical reality, how things really are. The process of science takes into account the fallibility of humans who prefer to believe in a reality they make up. This slide shows the 5 components of the scientific method. Sometimes they are presented as steps. First you do this, then you do this, etc. But we don't operate in such a robotic way. Often science teams are doing 2 or more components at the same time, and some scientists or teams focus on just one component for their entire career. It is a community working together that makes progress. I start off with observe as number 1 in order of priority. Scientific knowledge is based on observations of nature. From observations of many different events and situations, scientists try to find patterns and create generalizations as to the underlying fundamental processes involved. We create an explanation that explains all the past observations and that also predicts new ones. Scientists will create models to help them focus on the basic fundamental processes. In this context, a model is an abstract construct or idea that is a simplified view of reality, not something made out of paper, wood, or plastic, or some good-looking person. For example, to describe the motion of dropping my keys to the floor, I'd model the keys as a hunk of metal of a given mass, the Earth as a point with all of the mass at the center, and the accelerating motion would be well described by Newton's law of gravity. That ignores the jagged edges of the keys, air turbulence, friction, the quantum mechanics of all the atoms in the keys, and more. Theory, in the scientific use of the word, is different than the everyday language usage today. Most people today use theory as just a hunch, guess, belief, or proposal. Science uses the original meaning of theory, a logical, systematic set of principles or explanation that has been verified, has stood up against attempts to prove it false. Scientific models and theories must make testable predictions. If an explanation is offered that has no concrete test that could disprove the explanation in principle, it is not a scientific one. This characteristic of scientific explanations is often the distinguishing one between scientific and other types of theories or beliefs, religious, astrological, conventional wisdom, etc. Do understand that a scientific theory can be incorrect, but still be considered a good scientific theory because it makes a testable prediction of what will happen under a given set of observing or analysis circumstances. In a physics class, students will learn the theory of gravity, explain such facts as the rate of acceleration of falling objects. In a chemistry class, students learn that atomic theory, quantum mechanics theory, explains the structure and behavior of elements and compounds. Computers, cell phones, and other technological wonders are the result of quantum mechanics theory. In biology, students learn that the theory of evolution by natural selection explains facts about genetics and other subjects. In astronomy, we also have the theory of general relativity and the Big Bang theory. Like any scientist, the astronomer makes observations which suggest hypotheses. These speculations are made into predictions of what may be observed under slightly different observing and/or analysis circumstances. The astronomer returns to the telescope to see if the predictions pan out or if some revision needs to be made in the theory. Theory and observation play off each other. Experiments are the careful observations of nature. Experiments determine scientific truth. Experiments are the sole judge of scientific truth. The scientist usually learns about nature by using controlled experiments in which only one thing at a time is varied to determine whether or not a particular situation, feature, or circumstance can be determined to be the cause of an observed effect. The experiments can be repeated by anyone as many times as they want to verify that the effect is reproducible. The discussion up to now has been based on a couple of closely tied assumptions. We assume, number one, that there are fundamental rules that nature follows, and number two, that there is only one real way that nature is and that nature operates. There are rules, and nature, the physical world, always follows them. If we did not assume that, then it would be a waste of time to try to understand nature. Explanations and theories that correctly predict new results from new observations or experiments bring us closer to a true understanding of nature and the rules by which it operates. This true understanding of nature is what I call scientific truth in this course. In figuring out how nature works, we limit ourselves to purely natural explanations, that everything in nature can be described by using just matter, energy, and the interaction between the two. I like this quote from Eugene C. Scott. Most scientists appreciate that we do not yet understand everything there is to know about the natural world. But if a natural cause for something is not known, the scientific approach would be to say, I don't know yet, and keep looking. I distinguish scientific truth from other definitions of truth, such as religious truth, for example. Scientific truths are based on clear observations of physical reality and can be tested through observation. Certain religious truths are held to be true no matter what. That is okay as long as it is not considered to be a scientific truth. Some things like love, honor, honesty, and compassion are known to be right or true without the test of experiments. Conflict between science and religion often arises when people confuse absence of evidence with evidence of absence. Switching the words around makes such a big difference in meaning. Absence of evidence does not mean evidence of absence. I'm indebted to world religions scholar Houston Smith, who pointed this out in his book, The Soul of Christianity. The process or methodology of science restricts itself to natural causes. Scientists limit themselves to just matter, energy, and their interactions. This does not necessarily mean that scientists deny the existence of God or of things beyond the physical realm, because they understand the self-imposed limitation of the scientific method. Science can never prove the existence of God, nor can science ever disprove the existence of God. Yes, it is possible to be a scientist and a devout member of a spiritual faith. I know of many scientists who are serious practitioners of their religion. I myself am a practicing Christian who is active in a local church. It is possible to be both a believer in a religious faith and a scientist who agrees with the evidence of an old Earth and universe, billions of years old, and that life has developed and changed through the process of evolution, natural selection. For more of my views on the compatibility between religion and science, see my Science-Religion Interface resources site. I'll be happy to talk to you more about science and religion in an office hour, but since this is a science class, I will focus on the scientific type of explanations. The fifth component is communication and peer review. Scientists need to communicate their results in as clear, logical fashion as they can, so that other scientists can validate the results. Communication happens through articles in science journals and science conferences, as well as phone and email. Communication also includes the general public. So every K-12 education and college degree includes some science classes. Because it is possible to arrive at various interpretations of the same data or facts, and because science is a human endeavor with all the human failings of ego, culture, and preconceived ideas affecting what we notice and assume, scientists are willing to have their ideas and explanations closely examined and tested by others, particularly by their peers, in a process called peer review. Science is a way of trying not to fool yourself. The first principle is that you must not fool yourself, and you are the easiest person to fool. This quote from Nobel Prize-winning physicist and science communicator Richard Feynman is about why peer review is a crucial part of the scientific method. He was talking to his fellow scientists, his peers, in a talk at the Galileo Symposium. They are the you in the quote. Peer review works best if the ones who critically analyze an explanation have an alternate explanation and try to poke holes in the other person's explanation. This peer review happens at science conferences and in the pages of science journals. A scientist will not try to have his or her opinion advanced by political means or legislated by politicians. The last line on the slide is where I get to toot astronomy's horn and brag a bit. Astronomy allows us to test our guesses of the rules nature uses. In fact, we get to test the assumptions I talked about a few minutes ago, that there are fundamental rules that nature follows, and nature always follows those rules. The light we see coming from all parts of the universe is encoded with information about the laws of nature in all those distant parts. Astronomers find that the laws of physics, of nature, discovered here on the Earth are the same throughout the cosmos. Furthermore, since the light has taken a long time to travel the really great distances to get to us now, the light is encoded about the laws of nature in all the different times in our universe's history. Astronomers find that the laws of physics have not changed. They have been the same throughout time. Scotty was correct when he said, "I cannot change the laws of physics, Captain."